Swayam Prabha. Digital India. Educated India.
In the previous lectures, we have dealt with forces which act on a point. So, for example, I took a mass on which a force was acting. Then we took trusses and dealt with forces acting on the joints of the trusses. So, for example, the one force could act here, one force would act this point, one force would act at this point, and so on. Similarly, when we considered frictional forces, we considered the forces as if they were acting at one particular point. However, in nature, the forces are distributed. For example, if I take an extended body and consider the gravitational force on it, on each point there is a force acting. Its net effect is felt at a certain point, which we know as the center of gravitation. Similarly, if I take a plate submerged, say in water, the force acting on it due to the pressure of water is also distributed. Not only it is distributed, its magnitude at different points. So, deeper you go, larger it is. Near the top, the force is not that large. So, these are the arrows that are showing the force due to the pressure. This is also a distributed force which varies with the depth of water. And now, we want to develop mathematical techniques to deal with such forces. In this lecture, I am going to develop concepts such as centroid of an area which is related to the first moment of area, and then see how these concepts can be applied to mechanics or statics in particular. So, let us start with the concept of the first moment of area. I am first going to give you the definition, and then later we will employ it in certain statics situations. Suppose I am given a plane area like this in a coordinate axis set x and y. I define the first moment of this area m x about the x axis as summation y I delta a I, where delta a I is a small area here, delta a I at a distance of y I from the x axis. So, what am I doing? I am taking small elemental area delta a I and multiplying it by the distance from the x axis and summing it up. In a continuous distribution, you know from your course in calculus, this is nothing but y dA. That is the first moment about the x axis. In a similar manner, we define the first moment about the y axis. This is the area, and I took a small elemental area here at a distance y I from the x axis and a distance x I from the y axis. This is x axis, this is y axis. Define my first moment about the x axis as y dA, and similarly I can define my, that is the first moment about the y axis, as summation xi delta ai, which in the limit of continuous area becomes x dA. These are the definitions. So, we have first moment about the x axis and first moment about the y axis. Using the concept of first moment, I can define the centroid of this area. Centroid coordinate x coordinate xc is defined as first moment about the y axis divided by the total area, which is summation x dA divided by A, and similarly the y coordinate is defined as mx divided by A, which is summation y dA divided by A. Now, let us do certain examples using these definitions to calculate these quantities. As the first example, I take a triangle one corner of this triangle is at the origin. This is the x axis, this is the y axis. The height of the triangle is h. This distance of the vertex from the y axis is a, and the other corner is at distance b. I wish to calculate its first moment about the x and y axis and its centroid xc and yc. So, let us do that. Let us first calculate xc, which is related to my divided by the total area, which is equal to integration x dA over the total area. To calculate x dA, or the moment about the y axis, let me take a small area dA like this, parallel to the y axis. This distance I will take to be dx. The height of this is y. From similarity of triangles, I know that h divided by a is going to be equal to y divided by x, and therefore, y equals h over a x. This is true as long as x is below a. For x greater than a, I take a small area here whose y is going to be different, and that also we can calculate. Let me now go on to the next page, so that calculations become more clear. So, this is the y axis, x axis, this is the triangle, this is b, this is a, this is h. One strip I took here, other strip I am taking here. For the first strip, I know that y divided by x was equal to h over a, or y equals h over a x, x less than equal to a. For the second strip, I am going to have this distance is x. So, I am going to have y divided by b minus x, that is this distance, y divided by b minus x is going to be equal to h divided by b minus a. B minus a is this distance, and therefore, y equals h over b minus a times b minus x. Now, I am ready to calculate the moment about the y axis. The moment about the y axis, my is equal to integration x dA, which I am going to write as integration x y dx, where y dx represents the area of this strip or this small strip. This I am going to divide into two parts because behavior of y with respect to x is different for x up to a and for x greater than a. This, by the way, is for x greater than a. So, I am going to write this as integration 0 to a x y up to a, y is h over a x dx plus a to b x h over b minus a b minus x dx. That is m y, and you calculate this, the integrations you can perform easily. You get an answer for m y. Let me make the figure again. This is b, this is a, this is the height h, this is the x axis, this is the y axis, and for m y, which I wrote as 0 to a x h over a times x dx. Let me see, I indeed wrote h over a, yes, and plus a to b x h over b minus a b minus x dx, and when you do this integration, it comes out to be h b divided by 6 times a plus b, and therefore, x centroid is equal to m y divided by the area, which is h b over 6 a plus b divided by h b divided by 2, and this comes out to be 1/3 of a plus b. That is the x coordinate of the centroid of the triangle. Let us now calculate the y coordinate. Again, I make this triangle x y b a h, and to calculate the y coordinate, I take the elemental area dA like this. Recall that y c is equal to m x divided by the area, which is integration y dA divided by the area. So, at a height y, I take this is small strip, multiplied by y, and then calculate the area. You can see from similarity of triangles that I am going to have y h minus y, this is h minus y divided by h is equal to the width of this strip, which let me call delta x, divided by b, and therefore, delta x is equal to b h minus y divided by h. This is the length of this strip, and therefore, we can write, let me make the picture again. I am taking this strip, I am not writing b and a this time. We got h minus y divided by h equals delta x divided by b, and m y or m x is going to be equal to y dA, which I can then write as y delta x dy, y varying from 0 to total height h, and this comes out to be y delta x is b over h, h minus y dy, and you do this, this comes out to be b, y varies from 0 to h, this comes out to be b h square over 6, and therefore, y c is going to be m x divided by the total area, which is b h squared divided by 6 over b h divided by 2, which comes out to be h over 3. So, we have calculated the centroid of a triangle, and what is it? It is for a triangle which is given like this, with this distance being b, this being a, this height being h, the x, y, the x coordinate is 1/3 of a plus b, and y coordinate is equal to 1/3 of h. You can see that y coordinate is 1/3 of the height and x coordinate is 1/3 of b plus a. So, suppose I had a triangle like this, an area which is triangular of this shape. In that case, a and b are going to be the same, so that xc in this case would become 2/3 of b or 2/3 of a, and yc is obviously equal to h over 3. So, we have calculated the centroid for a triangle. As a second example, let me take a semicircular area like this of radius r. So, obviously, its diameter is 2r. This is the x axis, this is the y axis, and I wish to calculate its centroid. From symmetry, you can make out that the centroid must be on this axis somewhere, but I want to explicitly calculate it to show you how to do it. So, again, x c is going to be equal to m y over the total area. To calculate m y, we do integration x dA over the area. To calculate the dA, I take a strip like this, which is a vertical strip at a distance x from the y axis. You can see that dA in this case therefore is going to be the area of this strip, which is y dx, and therefore m y is going to be integration x y dx, x varying from 0 to 2r. What about the value of y at a given x? The equation of the circle whose center is at r and y 0 is going to be x minus r square plus y square equals r square, and therefore y is equal to square root of r square minus r minus x square, and therefore m y for the semicircle area is going to be equal to, this is 2r integration x y is square root of r square minus r minus x square dx 0 to 2r. Let me take r minus x to be equal to r sin theta, so that x equals r minus r sin theta. In this case, dx is going to be equal to minus r cosine theta d theta. Substituting this, we get m y equals, when x is 0, sin theta is going to be 1, and therefore theta is equal to pi by 2. When x equals 2r, sin theta is going to be minus 1, and therefore this is going to be minus pi by 2. X is r 1 minus sin theta, x equals r 1 minus sin theta, times r square minus r minus x square is going to be r cosine of theta, and then for dx I have minus r cosine of theta d theta. Because of this minus sign here, I can write this as minus pi by 2 to pi by 2 r cubed cosine square theta minus sin theta cosine square theta d theta. This is a simple integration which we can perform. So, I have my for the semicircle of diameter 2r my equals integration minus pi by 2 to pi by 2 r cubed cosine square theta minus sin theta cosine square theta d theta. Cosine square theta sin theta is an odd function with respect to theta, and therefore this integration sin theta cosine square theta d theta minus pi by 2 to pi by 2 is going to be 0, because as you go from theta to minus theta, this integrand changes sign, and integration cosine square theta d theta minus pi by 2 to pi by 2 comes out to be 1 plus cosine 2 theta over 2 d theta minus pi by 2 to pi by 2, which is nothing but pi over 2. And therefore, we get my is equal to pi over 2 r cubed, or x c, which is my divided by the area. Area is pi r square by 2. So, pi r cubed divided by 2 divided by pi r square by 2 equals r. So, as we noticed earlier, the x coordinate is on this axis. This is r. How about the y coordinate of the centroid? Let us calculate that. To calculate the y coordinate, I take a strip like this at a height y. So, y c is nothing but m x divided by the total area, which is integration y dA divided by the total area. Y dA, you can see, is going to be equal to the area of this strip here, this one, times the y. Y, this strip area is going to be this, if this distance is delta x dy, and y varies from 0 to r. To calculate the value of delta x, we again use the equation for the circle, x minus r square plus y square equals r square, and that gives me x minus r is equal to plus or minus the square root of r square minus y square. I get two values of x, namely x1, which I have shown here, equals r plus minus the square root of r square minus y square, and x2, which I have shown here, which is equal to r plus the square root of r square minus y square. And therefore, delta x, again let me make this figure, this is x1, this is x2, delta x is going to be x2 minus x1, which is equal to 2 square root of r square minus y square. Remember, we are after mx, which is equal to y delta x dy, which in this case is therefore going to be 2 integration y square root of r square minus y square dy, y varying from 0 to r. Let us take y equals r cosine theta, so that mx becomes equal to 2 integration 0 to pi by 2 r cosine theta times r sin theta times dy is r sin theta d theta. So, we have this is mx equal to integration 2 0 to pi by 2 r sin theta r sin theta r cosine theta d theta, which is 2 r cubed integration 0 to pi by 2 sin square theta cosine theta d theta. Cosine theta d theta is d sin theta, so I can write this as, by substituting z equals sin theta, I can write this as 2 r cubed 0 to 1 z square dz, which is 2 r cubed divided by 3. That is mx, and therefore x y centroid, which is mx divided by the total area, is going to be equal to 2 r cubed over 3 divided by pi r square by 2, which is nothing but 4 r over 3 pi. Therefore, if I look at this semicircle, the semicircular area, its centroid is at a distance r and at a height of 4 r over 3 pi. Slightly 3 pi is roughly 9, so 4 r 3 pi is slightly less than r by 2, so it is somewhere here. This is xc yc. Having defined the centroid of a plane area and solved 2 examples, let me make a point about the centroid of a plane area, and that is that the centroid of a plane area is fixed with respect to the area. That means, no matter which coordinate system I calculate the centroid in, it will always come out to be the same point in the body or in that area. So, centroid of a plane area is fixed with respect to the area. And let us see how we can prove this. So, let us take 2 set of axes x, y with origin O, and another set of axes x prime, y prime with origin O prime. The O prime is shifted with respect to O by x coordinate A and y coordinate B. Let the centroid coordinate in O prime frame be xc prime, which is equal to x dA over the area, or rather x prime, and similarly yc prime is equal to integration y prime dA over the area, where dA is some small area given in this plane area which I have drawn here. Now, let us calculate xc, which is equal to integration x dA over the area, but I know that x equals a plus x prime, and therefore xc is going to be equal to a plus x prime dA over a. A dA integral, a comes out and integral dA is the total area, so this will come out to be a plus x prime dA over a is nothing but xc prime. So, you see, if I calculate the centroid with respect to a shifted coordinate system, the centroid shifts by appropriate amount so that to remain at the same point in the body, and similarly you can show that yc will be equal to b plus yc prime, which I leave as an exercise for you.